setting for the possibility. That doesn't do a handout.
Thank you. Thanks a lot. Thanks for coming. So it's a pleasure to be here, back in Cambridge. I spent some times here over the years, a few years ago. So it's always really nice to be back. So I'm a cosmologist. I trained as a cosmologist actually here in Cambridge. But since we are in the chemistry department, let me just tell you that being a cosmologist is actually a little different than, it's not going to work, than being, it's always do that. Let me see, this works. Okay, has the sharing stopped now? Yeah, so let me try to share again. Okay, let's see if that works better. Okay, it works a bit better. Now the joke is gone. So I'm not a cosmetologist. It's almost the same thing, although I think cosmology is much more profound. Cosmetology studies the beauty, cosmetology studies the universe of beauty, whereas as a cosmologist, I'm really interested in the beauty of the universe as a whole in the largest possible scales, bringing from the infinitely small to the infinitely large. And so that's why we're zooming out of the solar system. Here we're zooming out of the galaxy. We're going to zoom out of clusters of galaxies over distances spanning over millions of trillions of kilometers apart. And so on those very large distances, as large as, this is not quite as large as that, but it could be as large as the whole observable universe today. We do believe that we have actually quite a good handle on the composition and on the behavior of the universe from a fraction of a second after the Big Bang all the way up to date. And I'll explain why we think we do actually have a very strong handle on what's going on, what the universe is made out of, and its whole of evolution for most of its time. But let me just say that for me as a cosmologist, it's actually useful to zoom on the largest possible scales and really look at the universe as a whole, taking away all sorts of different complications. So people ask me often why I am a theoretical physicist, why I want to study the universe as a whole, as opposed to much more interesting systems like galaxies or even chemistry or even life on Earth. And actually, it's much simpler to look at things on the largest possible scale. So you take away any kind of complications, and you're really trying to connect the behavior of the universe with some of the fundamental laws of nature. Now, to understand how the universe is, what the universe is made out of and how it has evolved, what is its history, we are relying on a series of different types of astrophysical and cosmological probes that are relying on very different physics, very different underlying physics, very different kind of distance scales or physical scales in which we rely on them. From the cosmic microwave background on the scale of almost, not quite, but almost of the observable universe today, all the way down to much smaller scales at the level of clusters of galaxies or even within galaxies themselves. And so I'm not going to go through all of them in details, but just to give you a little bit of a taste of what it means to do cosmology, what we rely on, I'm going to focus on the cosmic microwave background, which you may have heard of, and on supernovae, particularly supernovae, because they're a very intuitive tool to understand how we can get a probe on the evolution of the universe. So you may have heard of the cosmic microwave background radiation. You've probably seen some of the pictures that are shown before on the previous slide. But to understand what it is and why we can rely on that to better understand the universe, let me just draw an analogy in a second between the surface of the cosmic microwave background surface and the surface of a cloud. So to better understand why this surface in the history of our universe is important, you may think of the universe having started very dense, very hot, and it was like a big soup of plasma in which the electrons and the protons were just running around. And so light, photons, weren't able to travel very fast before being scattered by charged particles around. And as the universe cooled down, it became larger, it cooled down, there came a point where the electron got trapped around the protons, and so creating some neutral atom. And from that point onwards, photons, so light, was free to propagate. So from that point of surface of last scattering, what we mean by that is the last time the photons that we observe from the sky has scattered with a big hydrogen plasma. And so you can think of this surface of last scattering or the cosmic microwave background that we see from the sky as the temperature of the sky from this period in the very beginning of the universe. And so it's a little bit as if you're looking in the sky, it's a cloudy day, and there's a cloud on the sky. You don't actually see inside the cloud, or you see the surface of the cloud, because beyond that, photons, light from the sun, is being scattered by the water molecules inside the clouds. And so you can draw an analogy between the surface of the last scattering, the cosmic microwave background in here. That's if you look in the past, if you look in the sky, you look in the past, you see the surface of our scattering. It's a little bit like seeing the surface of a cloud. And that tells us some elements which are actually very important in understanding of the universe. One of the things it tells us is that the universe is completely isotropic. And that is really remarkable. We can look in any kind of direction in the sky, and what we see is that the temperature of this surface of last scattering, the temperature of the cosmic microwave background, is absolutely identical in all directions in 1 part in 10 to the 5. So in 1 part in 100,000. So wherever we look at, we see over distances of 10 million billion kilometers, we see that the temperature of the sky is identical within an incredible precision of the order of minus 270 degrees Celsius, or typically we call this in degree Kelvins. I'm sure you're more used to that as well if you're a physicist. And maps that we see that you may have seen like this is a map from the Planck satellite. There is not what we observe at first sight. It is this constant temperature that has been removed everywhere. Exactly the same constant has been removed everywhere in the sky. And once you remove this completely constant temperature, you see very tiny fluctuations in 1 part in 100,000, which statistics are completely consistent with our understanding of how the universe has evolved since the very beginning of a period of inflation. So to understand, one of the things we can determine from that is that to understand why the universe looks so isotropic, and if we don't want to consider that we are living in a particular place in the universe, then it must be that the universe is also homogeneous. So to understand why the universe is so homogeneous and so isotropic, we need to postulate the existence of a period of very fast, rapid, accelerated expansion at the very beginning of the universe, so that our whole observable universe, wherever we look at in the sky, is actually coming from a very small region at the very beginning of the universe. And this very small region has been stretched to the largest possible scales that we see today. And this has really incredible consequences because it tells us that very small quantum fluctuations that were happening at the very beginning of the universe have been stretched into the largest possible scales today. And so any of the structure that we see today, the clustering of galaxies, all of this kind of structuring is actually following a pattern and following statistics which is completely consistent with the quantum fluctuation statistics that we would have expected. And so in some sense, we're all children of the quantum fluctuations of the very beginning of the universe. So this is the cosmic microwave background. It's one of the essential tools we have at our disposal in cosmology to understand how the universe is behaving and evolving. Another one of those probes, and I'll just go through 2 of those and then I'll move on. But another very important one of them is I don't know if I can take this off. You see it? I can't? No? Oh. Is it? No. Okay, so another essential probe that we have on the sky for cosmology are, here it's written type 1a supernovae, if you want. I'll shorten it for SN, for supernovae. So a supernova is an explosion of a star. Those kind of type 1a supernovae are particular ones. When the star explodes, it explodes with a particular pattern, a peak at a very specific frequency. So you see that the peak has a very specific frequency, which can be very well understood. Now, if that object, if the supernova is moving away from us or towards us, if it's moving with respect to us, and then by Doppler effect, which I'm sure you heard about, then you'll have the frequency of the peak will be distorted in the way we observe it. So if the supernova is moving away from us, we will have the impression that we will observe the frequency of the peak of the explosion to be going towards a lower frequency, therefore to go towards the red if it were real colors. And so we say that the peak gets redshifted. And so by looking at the redshift of the peak, of the signal on an explosion of a star, a supernova, we can determine the velocity of the star as a function of its distance from us, if we also determine the magnitude of the environment in which the supernova is in. And so with those kind of observation, what we see is that the further away we look, and the fastest objects seem to be moving away from us. And this happens, again, completely isotropically in all possible directions. And so if you draw a pattern like this, which is a Hubble diagram that has been done almost, not quite, but almost 100 years ago, you can see that as a function of distance, which is here measured in megaparsecs, you see that the speed of the objects is going faster and faster. And so these are from type 1a supernovae, as well as all sorts of other type of observations. And so what it means is that not that we're living again in a particular place in the universe and everything wants to go away from our particular position, but rather that our universe is expanding. Really what it means is that space between any 2 points in the universe, in particular space between us and any other object in the universe, is being stretched. And the further away an object is, the more space there is that it has been stretched, and so that objects seem to be moving away from us faster and faster the further away it is. And so we understand that we live in a universe which is expanding, and we understand that from the Big Bang there may have been a period of accelerated expansion, and then that expansion stopped accelerating, and we would have expected, as we go further and further in time in the evolution of the universe, that even though the universe is expanding, there should be a gravitational attraction within all the structures being present in the universe that should make this expansion of the universe slow down. At least this is what we would have expected if the original picture that I showed you before was correct, in where most of the energy budget present in the universe was confined in these clusters of galaxies. And at the very beginning, the movie I showed you, you see some blue structure. This was just an animation that corresponds to dark matter being filaments in which clusters of galaxies are being confined. So if it was true that most of the energy budget present in the universe is confined in these clusters of galaxies, what we would have expected is, as we go and look in the past, or as we go and look at further and further distances, it should have been that the expansion of the universe was going faster. And so we would have expected that if I take this Hubble diagram and I look at further distances away, I look more and more in the past, then the expansion in the past should have gone faster, because we'd have expected the gravitational attraction between those structures to slow down this expansion. But what we do know, and what has been confirmed with nowadays very good accuracy, particularly with supernovae since now 25 years ago, is that exactly the opposite is happening. The expansion of the universe today, well, in the last few billions of years, is not actually slowing down, it's going faster and faster. And it's contrary to what I would originally have expected if this original picture was correct. And this is not just relying on supernovae, for instance, or the cosmic microwave background. There's lots of other probes, for instance, the current distributions of the clusters of galaxies. So we call that the large-scale structure of the universe. Gravitational lensing, so the lensing of light through the universe is a strong lensing, but we can also understand the effect of weak lensing of light as it propagates through the universe. And so all of those observations rely on very different scales, physical scales and energy scales, very different time in the universe, and they all converge to the same, they all converge to the same points in this understanding of the universe in overall. So I'm going to tell you in a second what those things are. But if you look, I want you to understand here is that if you look at the cosmic microwave background, if you look at the structure, the clustering in the universe, if you look at the supernovae, they could have given you quite different pictures, but actually they all seem to be converging into our standard model of cosmology. And nowadays, there's a wealth of all sorts of different data, which all, again, seem to be converging with understanding that the universe is not only expanding, it was accelerating at the very beginning of the universe. Then this acceleration slowed down, it stopped accelerating, but nowadays we see that the universe is accelerating again. And you may have heard on all sorts of type of tensions, for instance, the Hubble tension. It is true that we're starting to see some small discrepancies between some of those observations, but none of that fail the fact that we do see that the universe expansion is currently accelerating. There's still a huge level of agreement between all of those observations. So what we do see, all of those observations converge to the fact that 70%, it should be 76% of the energy budget of the universe must be made out of something that explains the late time acceleration of the universe. All the matter that we know of, all the matter that you and me are made out of, well, of course, we're not ordinary in any sense, but we are ordinary matter in the sense that we know what we are. We are only corresponding to 4% of the current energy budget of the universe. And I do accept the existence of dark matter. I'm even going to take it for granted. It may not be so controversial. It may not be so surprising that there may be other massive particles out there with which we don't directly interact, but with which we will be interacting gravitationally. Even if we accept the existence of this dark matter, that will correspond to an additional 20% of the energy budget of the universe that can help us understanding the clustering and the structure of galaxies. But on scales much larger than that, we still need to say that the universe is dominated by an unknown type of energy, which we call dark energy for lack of a better name, which leads to the accelerated expansion of the universe. So to better understand the place of this new form of dark energy with what we do know exists, with the ordinary kind of matter that we are, and its effect on the evolution of the universe through gravitational effect, I'm going to go back to what we know we are made out of and the fundamental laws of physics that we understand very well. So you may have heard, sometimes you hear that gravity is not a force, gravity is the manifestation of the curvature of space-time. I'll mention that again in a little bit. But as a particle physicist point of view, it is still true that you can think of gravity as the mediation of a force, mediated by a particle, just like the other fundamental forces of nature, in particular the electromagnetic force, the weak force, and the strong force. And all of those fundamental forces, in addition of gravity, explain all of the fundamental phenomena that we know exist. However, the matter constituents of what we know exist only correspond to 4% of the energy budget of the universe. What we know exists in here are all the fundamental particles of the standard model of particle physics, and we know that they interact through those 4 fundamental forces. Actually, we have very strong reason to believe that all of those fundamental forces of nature are fundamentally unified into one big theory of everything that includes gravity, it includes quantum gravity, and includes all of the other phenomena. We know that we have very strong reasons to believe that this is the case, even though we don't precisely know what this theory of everything is. But we know, for instance, that if you just take electricity and magnetism, and you've probably seen that already, they're not completely disconnected phenomenon. They are a unified phenomenon under electromagnetism. And what you consider being an electric phenomenon may be a magnetic one, depending on your perspective, particularly if different observers are moving with respect to one another. And we understand that electromagnetism, you can think of it as the theory of the electromagnetic force, which is mediated by light. Light is the mediator of the electromagnetic force. We know that even though you can think of light as an electromagnetic wave, deep down, this electromagnetic wave is carried by a fundamental particle, which we call the photon. So if you take a light of a particular color, and you reduce its intensity as much as you want, you'll see that you can't completely reduce the amount of energy carried by this wave at wish, in a continuous way. It carries an amount of energy which is proportional to what is carried by one photon or two photons, but nothing in between. It is quantized fundamentally, and this quanta amount of energy carried by any wave of light of a particular color is called a photon. And we know that this quanta of energy can be emitted or absorbed when electrons change energy levels around the atoms. Now we know that this is not all. We also know that we can take the electromagnetic force and you can also unify it with the weak force to lead to an electroweak theory, unified theory. This is thanks to the work of Glashow, Salam, and Weinberg. We know that the weak force is unified with electromagnetism. And just like we can understand that the electromagnetism is carried by a fundamental particle that we call the photon, the weak force is also carried by fundamental particles that we call, it's less interesting as a name, the W and the Z bosons. And we know that the W and Z boson exist, but we also know that we're less familiar with the weak force because the weak force is weak. Most of our interactions in our everyday life is through a messenger of light, is through electromagnetic interactions. We're not as used in everyday life. We're used in the sun or in other phenomena, but in everyday life, we're not as used to the weak force because the weak force itself is weak. And the reason the weak force is weak is because the mediators of that force, the W and the Z bosons, are massive particles, and so it's much harder to give them some dynamics, it's much harder to excite them, it's much harder to make them carry this force at larger distances. Nowadays, actually, we understand how the Higgs field, the Higgs mechanism, the Higgs fields which has been discovered in 2011, led to the Nobel Prize of Physics the year after, is the mechanism responsible for giving a mass to these fundamental particles, the W and the Z boson. We understand that thanks to the Higgs mechanism giving a mass to the W and the Z boson, this limits the range of the weak force and is responsible for the weakness of the weak force. While electromagnetism, which is carried by a massless particle, the photon, has an infinite range, so it does fall off as a Newton square law, but when you multiply this Newton square law with the square of the distance, so by the area, you get a complete constant. So in that sense, electromagnetism has an infinite reach. While we understand that this is the case because the particle that carries it is a massless particle, the photon, we also understand that because the W and the Z bosons are massive particles, they lead to a weak force, which is weak and has a finite range. So it falls off far faster. At some point, even if you multiply it by area, it still switches off completely, and we're not experiencing the weak force in our everyday life in human distances. So the weak force only operates in subatomic scales, and beyond that, it switches off completely. So the Higgs mechanism is responsible for the weakness of the weak force. This is a lovely picture of Peter Higgs when he came to visit our postdocs and students at Imperial a few years ago. And I think it's quite lovely because it kind of really represents the nature of the Higgs mechanism in how the presence of this of Higgs in here is actually what attracts interactions with all sorts of other particles around him. Actually, the Higgs mechanism should really be called the Kibble-Gronick-Handler-Brout Higgs mechanism. They are all here now aside from Higgs. And they understand that the Higgs mechanism is related to interactions at the level of quantum fundamental particles. And so to understand a little bit what we mean by that, I could have taken a picture of this lecture room, but I didn't have it ahead of time. So I've taken a picture of the Royal Institution lecture. And let's just imagine that you take everything out of this room. So just remove everything physically that you can consider being tangible out of this room, and then shield this room in such a way that there's no cosmic ray, there's no light, there's no gravitational waves, there's no energy from the outside that ever enters this room. So you create the best possible vacuum that exists in the universe, even better than a vacuum in outer space. And what you do know is that even in the best vacuum, you're not completely empty. You can never remove those quantum vacuum fluctuations. And in fact, the Higgs mechanism is the proof that even the best empty space is filled with quantum fluctuations, in particular of that of the Higgs bath that fills every pocket of the universe. The discovery of the Higgs and our understanding of how the Higgs mechanism works is the proof that empty space is still filled with energy, is filled with the energy of the quantum Higgs bath. And in fact, we do know that it should be filled with the energy of all of the quantum particles that we know exist. So there is a quantum vacuum energy. Now we understand from the Higgs mechanism, for instance, that light particles, like the neutrinos themselves or like light themselves, they interact very weakly with this path. And so this path doesn't impinge their dynamics. They can propagate for very large distances, while more massive particles, like the W and the Z boson, interact much more strongly with this path. And that's how the Higgs mechanism impinges the dynamics and therefore impinges the range of the weak force. And now we know that this Higgs bath, this quantum vacuum of the Higgs, and it should be of all the particles that we know exist as well, has an effect on other particles, for instance, the W and the Z boson, and it should also have an effect on gravity. So what I like to understand for the remainder of this discussion is how this quantum vacuum, for instance, the Higgs bath, has an effect on gravity, has an effect on the structure of space-time, and therefore has an effect on our universe. So if we go back to this picture we had before, which is a picture, this is an animation of the structure of our universe on relatively large distances. Again, it's an animation, so it's not real colors. In blue, they are animation of dark matter, so they are filaments of dark matter. And inside, in brighter color, are clusters of galaxies which are embedded in these filaments of dark matter. So according to this picture, we may have the impression that most of the energy budget of the universe is under this form of matter in either the filaments of dark matter or the clusters of galaxies. But it should be that if we were to zoom into a completely empty pocket of the universe, into what we call a cosmic void, and most of the universe is actually filled with these cosmic voids, which can be millions of light years across. So that means that it will take you millions of years to communicate with the closest galaxy. Those cosmic voids are completely empty of anything, of any black hole, of any dark matter, of any dust, of anything at all. And yet this should still be filled with this quantum bath of I don't know why I did that, but let me go into a second. It should still be filled with this quantum bath of all the particles that we know exist, and in particular of that of the Higgs. So if I were to zoom into any region of the universe, they should be completely filled uniformly throughout the universe, not only in the cosmic voids, but everywhere, in here, near the sun, near a black hole, at the very beginning of the universe, at the moment here, in the middle of emptiness, with its completely constant and uniform vacuum quantum energy. And so really what we like to understand is what is the effect on the very structure of space-time, on gravity into the universe. So you've probably seen a picture like this before, where we understand, and I mentioned it before, we understand, thanks to Einstein's theory of general relativity, that you can think of gravity as the manifestation of the curvature of space-time. You can think, for instance, of the Earth, the presence of a mass like the Earth, as curving the structure of space-time around itself. And now anything, anyone is living on that space-time, is experiencing this curvature, and that's how they feel the gravitational attraction of the Earth or to the Earth. And if you have a bigger mass, you'll have a bigger curvature, you'll have a bigger gravitational attraction. So now we understand what happens, according to Einstein's theory of general relativity, when we have one localized mass here, for instance, the Earth, and I can do it with the Earth and the Sun, and I can do things which are very complicated with clusters of galaxies if I want to, but these are still localized kind of matter. And that picture with this well here, this gravitational well in here that you may see, this is very specific to localized matter, the localized masses, where they are only at one point, or localized point in space, and then they live for a long period of time. But with this quantum vacuum bath, actually what happens is that they're not just at one point in space, they fill the universe completely at all points in space and at all points in time. So not only they have an effect like you would have think of a localized mass, which is present at any point in time, they also have the same effect along all spatial directions. And I don't know how much you've heard about special relativity or general relativity, but sometimes the effects that happen in time are opposite to what happened in space. And so even though for a localized mass, according to Einstein's theory of general relativity, it leads to this gravitational attraction that we all understand very well how it works, for a vacuum bath, which fills every direction in space and in time, the effect it has in time is also opposite to all of the three directions it does in space. And so the gravitational attractive effect of this quantum vacuum bath is actually to stretch the structure of space-time in every direction. We're not localizing this quantum bath in one point in space in the universe for all time. We're doing it for all time and all directions in space as well. And so the effect, the gravitational attractive effect of this quantum vacuum bath on the evolution of the universe is actually to stretch the very structure of space-time faster and faster, and therefore leading to an accelerated expansion of the universe. So you may have thought that it is paradoxal that we're living in a universe which expansion is actually accelerating, but if you take Einstein's theory of general relativity, according to which anything, any mass, any energy, any pressure, anything has an effect on the curvature of space-time, and you add to it precisely this quantum vacuum energy that should be present, the Higgs mechanism tells us that something like that should be present as well, then we actually lead to an accelerated expansion of the universe, in fact, exactly as we observe. We do observe that the universe is in a period of accelerated expansion. So now what we can do is simply do a back of the envelope estimation into how much quantum vacuum energy there is, and if that's enough to explain the late time acceleration of the universe. So I'm just going to do an estimation in here. It's not going to be completely precise, but it's going to be sufficient to give me an order of magnitude and understand what is going on. So let's imagine you have this quantum vacuum bath, and you have quantum fluctuations popping in and out of existence. Now, if I consider those quantum fluctuations coming from the Higgs particle, the Higgs particle has been detected, and we know that it has a mass of roughly 125 giga electron volt. So G gas 10 to the 9 electron volt. This is particle physicist energy scales. If you prefer it as a real notion of mass, then it's actually very small for my everyday life, but from a particle physicist point of view, that's a very large amount of mass. Because this amount of mass, or I can translate that in an amount of energy, is confined into a region of space which is inversely proportional to the mass of the particle itself. So you may have seen that there's a particle wave duality, as I mentioned before. If you think of a wave, the Higgs itself, you can think of it as a wave, and the wavelength of this wave would be related to the inverse mass, to the quantum wavelength of the particle itself. So I can imagine that the quantum vacuum is filled with those fluctuations, which have an amount of energy related to the mass of the Higgs, let's say, within a region of space which is related to the quantum wavelength of the particle, or the inverse of the mass of the particle. In this case, it's a very small quantum wavelength of the order of 10 to the minus 18 meter. So just for reference, our water molecule is of the order of 10 to the minus 10 meters. So this is roughly 8 orders of magnitude smaller in distance. So even though the amount of energy carried in any of these fluctuations is extremely small, if I just take into account the Higgs, it's actually in a very small region of space. And so the energy density, the energy per unit volume carried in that little box becomes extremely large. If I divide the amount of energy with the volume of the box, so this is the energy density contained in that box, and therefore contain the energy density contained everywhere in the universe, that corresponds to a huge amount of energy, 10 to the 29 kilogram per meter cube in normal everyday scales. Now, if I want to compare this amount of energy density that I would have expected the quantum vacuum to carry, based on any of our understanding of particle physics, with the actual amount of vacuum energy density I would need empty space to carry to explain the late time acceleration of the universe, I see that to explain our observations, we would need an energy density which is rather extremely small. There's 57 orders of magnitude difference between the two. In fact, when you take two of the pillars of modern science, two of the pillars of modern physics, I would say, gravity and cosmological observations relying on it on one side, which tells us that the universe must be filled with some dark energy, which has an energy density of the order of 10 to the minus 28 kilogram per meters cube. And then you compare it with expectation from the other pillar of modern science, the quantum field theory that leads to all of the standard model of particle physics that has been completely led to all possible discoveries of the past century, that leads to an expectation that the vacuum should be filled with some quantum energy which is constant, which behaves like dark energy, that leads to an accelerated expansion of the universe, and yet the amount of energy density being carried in here is extremely large. So there's actually, 57 orders of magnitude discrepancy between our expectations from particle physics and our observations on the evolution of the universe. This is the biggest discrepancy in the whole history of physics. This is the biggest discrepancy in the whole history of humanity. The vacuum energy that we would expect it to be present in quantum fluctuations is at least 57 orders of magnitude too large. We would have expected, based on expectation from particle physics and the quantum vacuum, that the universe should have been accelerating 18 orders of magnitude faster. So that would mean that if you take the space between any two of you and you were to put into account this amount of vacuum energy, it would lead to a stretching of space which would be so fast that any two of you would see the other one going faster than the speed of light. So that would mean that nothing in the universe would ever have been created. There would have been no structure formation. There would have been nothing at all. So clearly that cannot be the case. So in reality, we often phrase the question of vacuum energy or the dark energy or the accelerated expansion of the universe as a puzzle that the universe seems to be dark to us. As a puzzle as to why the universe is so dark, why are 70% or 76% of the energy budget of the universe made out of this new kind of energy. But the real question is not why the universe is so dark. The real question is why isn't the universe way, way, way darker to the point where we shouldn't even exist? There shouldn't have been any galaxies to talk about, any structure to talk about. So, plagued with one of the most fundamental questions of modern physics, typically the approach that has been taken is to say that this problem of the quantum vacuum energy, or called sometimes the cosmological constant problem, because this quantum vacuum energy behaves like a cosmological constant. It's constant everywhere in space and in time. So it's a constant cosmologically, it's a cosmological constant. So the approach that is typically taken to tackle this cosmological constant is simply to ignore completely this quantum vacuum energy. Is to say this problem is so big, it's so puzzling that I'm surely missing something. There must be a symmetry on another. There must be something else that comes into play, which I have no idea about. And so I'm going to ignore that problem. The question of the effect of the quantum vacuum energy has been known since the 30s, the last century 30s. And already then it was known, the Higgs wasn't discovered, but people knew about the electron. Already then people knew that the effect of the quantum energy of the electron should lead to a stretching of space-time, to an accelerated expansion of the universe, which would be way too fast. So at the time, people didn't know that the expansion of the universe was accelerating, and so the solution of the time has simply been to set that huge quantum vacuum energy to zero. And since 25 years or so, we have actually discovered that the expansion of the universe is accelerating. What people have done instead is postulate the existence of a new kind of energy that would explain the accelerated expansion of the universe. But we already know from the outset that there is something that should be present that should lead to an accelerated expansion of the universe. The only reason we're not using that is because the amount of acceleration it leads to is way too fast. So what I like to do in the last few minutes that I have is instead tackle the problem at its core. I'm not going to ignore the existence of this quantum vacuum energy. I'm going to account for it. But rather, I want to understand if there's a way for this quantum vacuum energy, for this Higgs bath, if you want, to lead to an accelerated expansion of the universe, but not as fast as I would have anticipated according to Einstein's theory of general relativity. Because after all, we are using Einstein's theory of general relativity to understand what the effect of this quantum vacuum energy should be on the largest possible scales of the universe. But we have no other test of Einstein's theory of general relativity on those scales. We have very strong tests of Einstein's theory of general relativity here on Earth, in the solar system, in the galaxy, but not on the largest possible scales of the universe. According to Einstein's theory of general relativity, gravity, the gravitational phenomenon, just like in electromagnetism, is a phenomenon with infinite reach. That's because the particle that carries it, the fundamental particle that mediates the phenomenon of gravity, that mediates the force of gravity, that particle is called the graviton, according to Einstein's theory of general relativity, is a massless particle. And so like for electromagnetism, it should have an infinite reach. And so that means that if I take two, let's say, galaxies or clusters of galaxies located on the other side of the observable universe from one another, this is 10,000 billion trillion kilometers away from one another, still technically they exert a small gravitational attraction in each other. That gravitational attraction is extremely small, is completely irrelevant, but what's important is that to understand the dynamics of the universe on those scales, we also need to account for all of the quantum vacuum energy present in between. And this is really what makes a huge effect. Locally, the effect of the quantum vacuum energy is small, but because most of the universe is empty, over those large distances, the effect of this vacuum energy is absolutely vast, is absolutely large. But it could be that gravity is not as doesn't have as large a range as only expected according to Einstein's theory of general relativity. We already know, thanks to the Higgs mechanism, that there are some particles in nature, like the W and the Z boson, which have a mass. And the presence of this mass for those particles is to limit the range of the force that they mediate. So could it be that the gravitational force is very similar to what is expected according to Einstein's theory of general relativity, but if the particle that carries it had a mass, then the range of the force of gravity will be finite. Of course, we wouldn't want it to be as small as the range to be as small as that of the electroweak force, of the weak force. Otherwise, of course, gravity will switch off on subatomic scale. We want the range of gravity to be larger than the Earth, larger than the solar system, larger than the galaxy, larger than a cluster of galaxies. But it could be that on very large distances, on large enough distances, gravity actually switches off. So this should be close to very cosmological distances, and the effect we will start seeing today is that not all of the quantum vacuum energy present in the universe should lead to the accelerated expansion of the universe. Just a much smaller amount of it, because beyond some given reach, gravity switches off, and so the effect of this vacuum energy is limited. Its impact on the evolution of the universe is limited. In fact, the idea that gravity could potentially be a phenomenon with a finite reach is something which is very natural. Even Newton himself, when he came up with Newton's square law, his range of the gravitational force, he contemplated the possibility in a Newtonian sense that gravity could have a finite reach. And Laplace contemplated that possibility as well. And when it came to the last century, where we understood that we could describe gravity not in a Newtonian way, but according to Einstein's theory of general relativity, and that we could think of gravity as being mediated by particles, so adapt general relativity with the quantum realm of particle physics. Pauli himself, who's one of the founders of quantum mechanics, contemplated the possibility that gravity could be mediated by a massive particle and therefore have a finite reach. And Salam himself, who is one of the founders of the electroweak phenomenon, we can say one of the founders of the particle physics, or the standard model of particle physics, contemplated the possibility that gravity could have a finite reach, or being mediated by a massive particle. But throughout the centuries, this possibility was always refuted because there was a fundamental instability in trying to make sense to a theory of gravity like Einstein's theory of general relativity, where the particle that carries gravity, the graviton, would have a mass. Until with our collaborators, Gregory Gabadazzi and Andrew Tolley, we finally find a way to constrain all of these instabilities in such a way that they would be decoupled and do no harm in the universe that we can observe. So I'm not going to go through the details of that. I can give you the references if you want to. I explain a little bit more in there. But for the last few minutes that I have left, what I thought I'll do is rather give you some indication of what it would mean observationally to consider a theory of finite range gravity. So when you consider a theory of finite range gravity, you don't only change the range of gravity. The way you do that, you affect different frequency of gravity in a slightly different way. And so, for instance, with future missions, this is LISA, future interferometers in space, we are hoping to observe gravitational waves with lower and lower frequencies, with larger and larger wavelengths. And when you're considering gravitational waves with large enough wavelengths, you would start expecting that the effect of the mass, gravity, or the effect of the modification of gravity on very large distances should start kicking in. And so in particular, if you imagine that you have, sorry, it's a bit hidden behind, use your imagination, sorry. If you imagine that you have two black holes merging and then colliding, and they affect the space-time around themselves so much that they produce gravitational waves, which will travel through the universe for millions of years before we reach them here on Earth. Let me run through that again. And as they do that, as they reach Earth, they will deform space in our instruments in such a way that you start seeing the gravitational wave passing through. So you'll see on the left here, these are the signal from the first gravitational wave detection in 2015. So for a particular event, if you are in a theory of gravity according to Einstein's theory of general relativity, where the graviton has no mass, where gravity has an infinite reach, this is the type of signal that you may expect. It will be exactly the same signal as what has been emitted, because all the frequency of gravitational waves will have traveled exactly at the same speed and exactly at the speed of light. But if you're considering a theory of finite mass gravity, of finite range, then at sufficiently high frequencies, at those frequencies, you would expect the gravitational waves to travel at the speed of light. And as you go to lower and lower frequencies, you start seeing a very small modification of the speed of gravitational waves. And so if the frequencies that are emitted before are lower, they travel ever so slightly slower than the frequencies that are emitted later in the signal that you will expect to receive will appear a little bit more compressed. Of course, this is very dramatically enhanced for effect, but actually from the very first detection of gravitational waves in 2015, the one parameter that they could constrain from looking at whether or not they could see a modification of the form of the signal, of whether or not they could see a modification of the dispersion relation. What I mean by that is of the speed of propagation of the gravitational waves depending on their frequency. The one constraint that they could put is a constraint on the mass of the graviton. They were able to put a constraint, thanks to LIGO, of the order of 10 to the minus 20 electron volt or so. But bear in mind that in order to explain the current observations, we will need a mass of the graviton to be of the order of the Hubble parameter today, which would be 10 to the minus 32 electron volt, with still roughly 10 orders of magnitude below what is currently observable with LIGO and such kind of interferometers. But we're hoping in the future, with space-based interferometers and other gravitational wave probes, to being able to probe gravity and the long range of gravity to a much better accuracy. So if you are curious on what this may look like, I haven't written down for you a theory of general relativity. This would, however, be what a theory of massive gravity would look like. Really, whether a theory of massive gravity has any chance of surviving the future test, that's for future generations or future tests to tell. The reality is, what's important is that the possibility is now open. We're here to explore what may happen in the universe. But what I found really interesting is that in doing cosmology and in understanding how the quantum vacuum fluctuation may affect the largest possible scales in the universe, what you try to understand is how the infinitely small may have an effect on the infinitely large, how quantum vacuum fluctuations that fills every empty pocket of the universe may have an effect on the largest possible scales, and that may be imprinted through this mediation on gravitational waves that we may be able to observe in the future. Thank you.
Question. Thank you for the talk. You just mentioned that we postulate that maybe the gravity switches off at a large enough distance. But does it mean that it goes to exactly 0, or it just tends to 0?
It's exponential. It's an exponential suppression.
Oh, that, well, the gravity's inverse proportion is square.
Yeah, yeah, yeah. So it's a much faster, it's a much sharper transition. So in the graph I have there, it's multiplied by the distance square. So you can't see, I'm sorry, it's written maybe in another plot I had it. Here it's multiplied by the area. What could you see that in one of the previous plot I had? So area, I mean distance square. So that's why for gravity, let me put it maybe in the other one I had. Okay, sorry about that.